You want to know something. Anybody has an answer? Yes?
Magnetism is a phase transition of the second kind.
Yes?
So the magnetic suspensivity divergence to the infinity.
Right.
At the Curie temperature.
Right.
So to solve this problem, the critical exponent is needed.
Yes, but you get the critical exponent, and then what? Then you can say, okay, I have a critical exponent, so I have magnetic ordering. But you don't need the critical exponent to arrive to the conclusion that you have magnetic order. If you measure magnetization, that is a very easy and direct measurement, and that is enough. You see? Because once you have a spontaneous magnetization, you know that you have a ferromagnet. You see the point? So, but if you want to go into all the troubles of then in my slides, it was said that critical exponents are independent of the spin value and of the magnetic anisotropy. But they were very dependent on lattice anisotropy or lattice value, lattice dimensionality, sorry, and spin dimensionality. Okay? So you need critical exponents when you want to see a change in lattice dimensionality or in spin dimensionality. Then you need it, because it is painful, but it's the best way to arrive to this knowledge. Okay? You got it? So, may I have it? So, in page number... In page number 444, oh, sorry, 9, no, sorry, I have to point to page number 9. Yeah, in page number 9, the first slide says that then, in cases of a spin anisotropy, lattice anisotropy, a crossover in the spin or the lattice dimensionalities may be observed. So to study this kind of crossover, where the system goes from low to high dimensionality or high to low dimensionality, when you start with an Ising lattice and you move, the system transform into Heisenberg lattice, you need to go into critical parameters to determine it. You see in the page 8, in the last slide, I said critical indices depend of spin dimensionality, lattice dimensionality. They should be independent of spin value, lattice symmetry. So anytime you want to see changes in a spin and lattice dimensionality, critical indices may be a good thing to study. Okay? Sorry. Okay. Well, you did some work. Thank you very much. And the best of it, you start interacting. That is very good. Now I think their arms are flexible and can get up, and this is very good. This is very good. Okay, so let's go very quick to remember the last is a bit. the end of the last part of the previous seminar, you remember we were talking about magnetism and disorder. So I will go very fast to this part. I will go into the example. I have pruned my example. My example was a full talk or half of the previous day seminar. I have pruned it much more just to give you an idea. And then we will go into neutron scattering, the fundamentals, and okay. And there will be time for questions and discussion. Don't forget. Time for questions and discussion. So I'll do as the undergraduate group, I ask them to think during the lecture one question, okay? In order to have it ready. And at the end of my lecture, I will ask any question. I want to see hand rising up, okay? Remember types of disorder. There was chemical disorder. There was the two-component system with chemical disorder. Was bond disorder. This is one-component system with the chemical, the bond disorder, and topological disorder. And you remember we were concluding that in magnetic systems, disorder affects severely the magnetic properties. So, because disorder modifies locally many parameters in the interaction Hamiltonian, and we were discussing these two types of interaction Hamiltonian, which in fact is the same, but this one applies better for organic materials and free radicals. This one is more general, how the disorder were affecting J and A and anisotropy and so on and so on. And then we arrive to the conclusion that disorder affects magnetic moments, magnetic interactions, symmetry. Because of that, we have magnetocrystalline anisotropy modified, locally modified, and we can have Dallo-Ginsky-Morillet interaction arising, which is a kind of Kantian. It's a term in the Hamiltonian that you remember I told you it tends to move the moments perpendicular. So now we have a lattice that prefer to be antiferromagnetic. When you introduce some disorder, you can make it to move some moments, turn to a canted situation, and because they are canted, can I use this? Because they are canted, you see this is one, the moments are like this, antiferromagnetic, but because the effects of disorder tend to move the moment into a canted situation, we have a net moment in the perpendicular direction. Okay? So the magnetic properties has changed.